Hello. Today I'll be presenting my machine learning project on predicting electrical energy output from a combined cycle power plant. I'll walk you through my model approach, demonstrate my final model, and explain how I evaluated its performance. Let me start with the project overview. I work with a data set containing 9568 hourly readings total, or 9,568 hourly reading totals. For my power plan, using four environmental variables to predict energy output ranging between 420 to 496 megawatts. So some of the key points to emphasize on this project are the fact that it's a large real world data set. There's practical applications behind it, and there are clear numerical target ranges to establish. So first, let me clearly define the problem. This is a regression task because I need to predict continuous numerical values for energy output measured in megawatts. Here's a sample of the actual data sets. My input features temperature in Celsius, ambient pressure in millibars, relatively humidity percentage in exhaust vacuum in centimeters of mercury. The target variable highlighted in gold is the net hourly electrical energy output. Since we're predicting continuous values rather than categories, this is clearly a supervised regression problem. I started with the exploratory data analysis to understand my features. Here you can see correlation matrix showing strong correlations between environmental conditions and energy output. Notice that exhaust vacuum has a strong negative correlation of negative 87 with energy output, while temperature shows a positive correlation of positive 0.65. This makes physical sense due to the fact that higher vacuum reduces efficiency. For my modeling approach, I split the data using 70-15-15 strategy, focusing on 70% on training, 50% on validation, and 50% on testing. I use the validation set to compare different models and reserve the test for final evaluation only. Now, the key part, model comparison. I evaluated three different approaches: linear regression, random forest, polynomial regression. First, linear regression, a simple baseline model that achieved an R square of 0.87 on the validation set. This gave you a solid foundation to compare against. Second, random forest. I use grid search to optimize hyperparameters, including number of trees, max depths, and minimum sample per split. This ensemble method achieved an R square of 0.93. Third, polynomial regression. I created polynomial regression features to capture nonlinear relationships, which achieved an R square of 0.91. Based on the validation performance, random forest performed best with 93.25% variance explained. So I selected this as my final method for my model. Here's my final model evaluation and test set that was never set during training. My random forest achieved excellence performance, an R square of 0.92, meaning it explains 92.7 percent of variance in energy output. This is excellent performance due to this is a real excellent performance for a real world regression problem. An RSME of 4.23 megawatts. This is the root mean square error representing the average predicting error, giving our target range of 420 to 496 megawatts. This represents less than 1% error. And MAE of 3.50 megawatts. This is the mean absolute error, which shows the typical prediction error rate. The prediction versus actual scatter plot would show points closely following the diagonal line, indicating accurate predictions across the entire range of energy outputs. Let me demonstrate the model with real examples from the test data. Here are actual predictions. For conditions with 15 Celsius temperature and 40 centimeters mercury vacuum, the model predicted 465.1 megawatts versus actual 463.3 megawatts, an error of only 1.8 megawatts. So as you can see here. Similarly, for 25 Celsius and 58 vacuum predicted 442.7 versus actual 444.4, which is 1.7 megawatts. The level of accuracy consisted within a deviation of 3 less or plus or minus megawatts, making this model highly practical for operational planning and energy forecasting. To summarize, I successfully built a regression model that predicts power plant energy output with 92.7 accuracy. My systematic approach of comparing multiple algorithms using proper validation ensured that I selected the best performing model. The random forest achieves an average prediction error of only 3.15 megawatts. The model correctly captures the complex relationships between environmental conditions and power generation, providing reliable prediction across all operating conditions. This enables accurate energy output forecasting for our power plant operations, supporting efficient grid management and energy planning with high reliability. Thank you for watching.